This video on nuclear chemistry. Nuclear forces are found in the nucleus, of course, and there's two main types that are impacting how the nucleus is able to stay together. The first one is the nuclear force, or the strong force, it's oftentimes called as well, and it holds neutrons and protons together. The other one is the electrostatic repulsion, and that's where protons that are all the same charge, all positively charged, tend to like to repel each other. And so when we're talking about isotope stability, stable isotopes that do not undergo nuclear change have nuclear force that's greater than the repulsion force, and unstable isotopes that undergo nuclear change or become radioactive have a repulsion force that's greater than the nuclear force. And that ends up resulting in radioactive decay in order to become more stable. And so that's what happens. Radioactive isotopes will decay until they get to be stable isotopes. And so what constitutes being stable versus unstable tends to follow along with this band of stability. And so what we see is that stable proton to neutron ratios, that it's all about the ratio of protons to neutrons, tend to fall between two areas. So the 1-to-1 ratio, if you see this line right here, this is the 1-to-1 of number of protons to number of neutrons in the nucleus. And so along that line, we see that lighter elements, things that have fewer protons, tend to be closer to that 1-to-1 line, and that's where they're most stable. And then heavier elements are along this 1 to 1.5, and so we see that the heavier elements tend to be closer to there. And then the ones in the middle, of course, are kind of in between there. And those are the most stable isotopes. The nuclei will decay to reach that stable ratio if it's not in a ratio that falls between those lines that are optimum for whichever type of element it is. If there's too many neutrons, they could undergo beta radiation, and too many protons, positron. We also have alpha decay as well. And so we're going to take a look at all three of those. So here's our types of radioactivity. So alpha decay is where we have two protons and two neutrons. So the P plus is a proton and the N with the little zero is a neutron, are going to leave the nucleus. And so this is a process where the nucleus of an atom is falling apart and parts of it are leaving this particular atom. And so if we have this particle, which is really a helium atom, okay, the number on top, it represents the mass, and the number on the bottom represents the protons, or the atomic number. So in this particular case, we see that the mass number is going to decrease. So this chunk comes out of the nucleus, and what's left over is going to be reduced by 4 mass numbers, and the atomic number is going to be reduced by 2. In beta decay, we see that a neutron turns into a proton and an electron. That electron is released or ejected out of the nucleus. It can't stay in the nucleus, but a neutron turns into a proton. We don't see that there's any change in the mass, and so there's no change in the mass. But we've changed a neutron into a proton, and so we're going to increase the atomic number of whatever this new substance will be after this by 1. Positron is actually the opposite of that, so that's where a proton is turning into neutron and an electron. Again, the electron will leave the nucleus, it can't stay there. Mass doesn't change because protons and neutrons are equivalent in their mass, but we're going to reduce our atomic number by 1. Finally, the last thing is gamma. You've probably heard of gamma rays before. They're just really high energy, and they really accompany whenever we have broken that strong nuclear force, that gamma energy or radiation is going to be released. And so they don't impact the mass and they don't impact the atomic number, but they tend to coincide with the other types of radioactive decay. So let's take a look at some example problems. And whenever these things decay, they're going to become something new. So we're going to use plutonium-244 as an example, and we're going to take it through all three types of decay processes. So in the first one here, we're going to have plutonium. So Pu-244 is the mass. Plutonium is always number 94 on the periodic table. So if you have yours nearby, you might check this. It's down in one of the bottom two rows on the very bottom of the periodic table. We always represent any kind of change with an arrow. So we're saying that this is going to change, and this is a nuclear change. And so when this changes, we're going to show, and I always like to write the particle first. You don't have to, but I like to write it first. In this alpha particle is going to be released. Okay, so there's my alpha particle, and that's come out of the plutonium, and so what's left over is going to have to be reduced by 2 for our protons, so it's going to be 92, and 4 for our mass, which is 240. Now, the 92 is what's telling us what element it is, and if we look on the periodic table, number 92 is uranium. So don't forget that the 92 is what's telling us that we have uranium. And so this plutonium has transmutated now through an alpha decay process into uranium, which is the new element. If we were to take that plutonium-244 and we were to apply a beta emission to it, we would have, we'll start the same way, plutonium-244, 94 on the bottom. We're going to represent our nuclear change with an arrow. And now we're going to see that beta particle. And then the new thing, remember, is we have a neutron that becomes a proton. And so we're actually going to increase our atomic number by 1, and it's going to be 95. We didn't change the mass, so it's 244. And 95 on the periodic table is Am for the symbol. Now it's interesting because when we look at balancing the numbers from each side, we have 94 for the total mass on the left-hand side of the arrow. And then on the right-hand side of the arrow, we have a -1 plus 95, which gives us 94. So our values, our total values, should be the same on both sides of the arrow. And that's kind of a consistent thing we see in chemistry. Our last one is going to be positron. So we're going to start off again with our plutonium, Pu-244, 94. And now, if we have positron, we're going to see the electron, and in this case it's a positive one because the proton turned into a neutron, and that electron that gets emitted, okay, so that's why we see emission rather than decay. It's still decaying, it's still changing, nuclear change. And so in this case, we're going to see this is going to go down by 1, so it's going to be 93. The mass doesn't change again, and 93 on the periodic table is Np. Okay, and we can double check. So on the left-hand side, we have 94. On the right-hand side, we have 1 plus 93, which is a total of 94. And the same thing goes for our values for mass. So on the left-hand side, we have 244 on each one of these. On the right-hand side, 244. And then in this top one, we had 240 plus the 4, and so that gives us a total of 244. I hope that's helpful and gives you a little bit of information about nuclear